Okay, so in this video, we're continuing our derivation of the D4h character table. This is part two. And what we did in the first video was part one video. If you haven't seen that, please go to it. We figured out that there's 16 different operations in the D4h point group, and that we can group them, that we should group them into 10 different classes. And the first rule of the character table is that the number of classes has to equal the number of irreducible representations. And so that tells us that we're going to have 10 different irreducible representations here. So I'm going to label those gamma 1 through 10. Now, later on, we will replace these with the Mulliken symbols using the Mulliken symbol rules. But for now, we need to figure out what the irreducible representations are before we can give them the proper Mulliken symbol labels. Another point to make here is that, I wrote these down in some arbitrary order here. Usually people start off with identity and then the principal rotation axis, but it doesn't really matter. You could scramble these. These are just labels, right? You can scramble these however you want. And same things with, how the columns are ordered and how the rows are ordered is totally arbitrary. Although you always see the same answers when you look up character tables most of the time, because people are just sort of copying from each other and not re-deriving them from scratch each time, like we're doing. So anyway, now that we got this, we got a 10 by 10 matrix. So we're dealing with 10-dimensional space here. So this looks pretty daunting, but turns out vis-a-vis some of the other character table derivations we've done, this is going to be relatively fast because there's a lot of one-dimensional irreducible representations. But we always start off with the totally symmetric irreducible representation, which is ones across the board. So I write 10 ones, there it's totally symmetric. Now from here, we can go and try to figure out, what this column is. So there's another rule in the character table, which says that the sum of the squares of the dimensionality has to equal the total number of operations in the point group. So in other words, in this case, 1 squared plus a squared plus b squared plus c squared plus d squared plus e squared plus f squared plus g squared plus h squared plus I squared has to equal 1 plus 2 plus 1 plus 2 plus 2 plus 1 plus 2 plus 1 plus 2 plus 2, which ends up equaling 16. Total order of the point group, total number of symmetry operations. And these are dimensionalities, so they tell us how many functions transform as this symmetry. So only valid numbers are 1s, 2s, 3, 4, or 5s. Okay, you're never going to have higher than 5s in chemically relevant point groups. And 3, 4, and 5s are really rare. Most of the time, you're going to have 1s and 2s. So you can stare at this for a while and see, what combinations of 1, 2, 3, 4, and 5s gives us 16. Obviously, you can't have a 5 that'll blast you off into 25 beyond 16. You can't have a 4 that'll blast you all the way to 16, and you already have 1, so that doesn't work. And you can't even have a 3 because that'll put you at 9. And then you have too many other ones that need to be 1, so that'll blast you past 16, right? Because you have 9 unknowns here. So if you put one of those knowns as a 3, that will put you at 10. And then you'll have another 8 unknowns that if all those are 1, that'll get you to 18. So that's above 16. So you're going to have 1s and 2s. If you stare at this long enough, what you're going to find is that basically you're going to have all of them equal to 1s except for 2 2s. Okay? And the way that that works is because you're going to have 8 1s. And so 8 1s squared is still 8. And then you have 2 2s that are squared. Well, each 2 squared is worth 4. You have 2 of them, so that's 8. So you have 8 plus 8 is 16. All right, so that rule, that's one of our character table rules, that allows us to put down numbers like this, all 1s and then 2 2s. Again, the ordering that I do this is totally arbitrary. I'm just going to erase this because we're going to need more space. And at this point, the best thing to do is to start testing various functions. And so a nice one to start with is always z. And so we'll test the function z, hoping that it's not equal, doesn't transform as a totally symmetric representation, but that it transforms as something else. So then we go ahead and we ask the question, how does the function z transform in all these different symmetries? And we can write our little axis here to help us visualize this. We're visualizing a z vector. I'm asking how does this z vector transform with all these different symmetry operations? One symmetry operation in each class, doesn't matter which one. So the function z, when you do identity on it, is going to go to z. Okay, and then we ask the question, what 1 by 1 matrix describes this transformation? And that is the matrix 1, right? Not very interesting. Z times a 1 by 1 matrix with the only element being 1, it gives you z back. We take the trace of this matrix, or the character of the matrix, and we symbolize the function character, saying character out by chi, Greek letter chi. The trace of this matrix is just a sum across the diagonals of this matrix. Well, there's only one element in it, so it's just one. There's nothing to sum, and so we get a value of 1 here. Okay, that's not very interesting. Now we keep going and we go C4. Well, C4, we do a C4 that's along the z-axis. So we're taking the z vector and we're rotating it 90 degrees, but we're rotating it right along the z vector. Well, it's in the z vector, so it's not going to do anything. It's still going to be pointing up. And because it's still pointed up, it's still defined as z. So z goes to z, and we'd have this exact same business where we have a 1 by 1 matrix, and we can say that the chi of the C4 operation is equal to 1. We could have done C4(3) as well. That's the other symmetry operation, remember, from the previous video in the 2C4V class, and we would have gotten the same answer. You rotate that 270 degrees, still going to be pointed up. So you're still going to get a value of 1 there, but I put a value of 1 there because we got a character of 1. Let's do the next operation, which is C2 class. Z goes to Z. And I'm not going to write this out again because it's the exact same thing. Z went to itself, so we get a 1. What about a C2 prime? Well, C2 prime, we could define it as it's 180 degrees in a different direction. Remember, we had this molecule here from the previous slide and in the previous video, and the C2 primes they're up here, we're 180 degrees going through the bonds. C2 double primes were bisecting. So we could define this as the x-axis. So now we're defining our bonds and our C2 primes as being on the x-axis. We're spinning it this way. So we're flipping this z vector down, right? And so that's going to take z into the negative of itself. And so this gets us a different answer here. There's going to be a 1 by 1 matrix, but the value now is -1 to take z into negative z. So the chi of C2 prime operation is -1. And so that's going to give us a -1 here. What about C2 double prime? C2 double prime is also going to take z into negative z, and let's understand why. Now we're not rotating there, but we're rotating, remember, at a 45-degree angle, right? So the axis that we're rotating along looks like this, right? But we're rotating 180 degrees there. Still, same thing. It's going to flip. We're rotating perpendicular to it. We're rotating something in the xy plane. So z is going to go into negative z. And so we're going to get the negative of that. And so for the same reason, we're going to chi of -1. I'm not going to rewrite it there. And we get -1. Inversion. Remember, the definition of inversion is it takes any arbitrary point x, y, z and goes to the negative x, negative y, negative z point. So you can see from here, z clearly went to negative z. So we're going to have there a -1. Huh? What about S4? S4 is our next one. That's a C4 followed by a sigma H. So we know from before that a C4 didn't do anything, so that went Z to Z. But what does a sigma h do? Well, a sigma h is perpendicular to our z. So that our sigma h is in the xy plane. So this z vector is looking, it's above the mirror plane, so it's going to look at itself coming below the mirror plane. So it's going to go into the negative of itself. And so what that ends up doing is taking z to negative z. Again, the C4 part we figured out didn't do anything, but the sigma h part right now we figured out did negative itself, so overall it does the negative of itself. And then we have the sigma h, and we just talked about that. Sigma h goes to the negative of itself. So that is z going to negative z, so we get a -1. What about the sigma v's? Sigma v, remember from the first video, is going along the axis, but it contains the z-plane. So because it contains the z-plane, it looks something like this, right? If we define it that way, as the bond be along the axis, that's what we did before. It's going to contain the z-plane. So whenever you have a vector or point in a mirror plane, it doesn't change. And so what that tells you is that for sigma v, z goes to z, and so we're going to get a value of 1, just like we had over here. And same thing is actually going to happen with sigma d, because again, it's in the mirror plane. It's going to be 45 degrees off, but it's going to be like this blue plane here. It'll look like this, and oops, not the best drawing there. Erase that bottom part. So it'll look like this. But again, that z vector is in the mirror plane, so nothing's going to happen. So what's cool about this is now we derived a totally new function, irreducible representation, right? Luckily, when we did this z function, we did not get something that was equal to 1s across the board. We could have, depending upon the point group and how the math worked out. But we didn't, and so that helped us get one step closer to deriving the character table. So we're 20% done. We've done 2 out of 10 of the irreducible representations. All right, so how are we going to do the next ones? Well, we just pick another function. And so actually, after we do z, I like to do x or y, it's fine too. So again, now we're looking at a x vector. It's not a z vector. We're asking the same questions. How do these different symmetry operations, one symmetry operation in each class, how does it transform? Well, identity, x goes to x. C4, x is going to spin around 90 degrees, and if we define it as going this way, it's actually going to spin over there. It spins into the y vector. So x goes into y. That immediately tells us that we can't define the x vector solely in terms of x or negative x, in terms of itself. We have to invoke y. So we can't, so x and y, in other words, are going to transform together. And what this tells us is that we actually put this in the wrong spot here because it's a two-dimensional vector. We have 2 vectors, so it's going to be one of these 2s. So let's put x and y together. And x goes into y. And y, where's y going to spin? If we're thinking about the y vector, y is going to spin into the negative of itself, right? The negative of x, sorry. So here was our y vector. Let's say this is y. It's going to spin there. This was x. So y is going to go into negative x. I got the text back. So x went to y, and then we just figured out that y went to negative x. Okay, and so because we have this two-dimensional matrix, in both of these cases here, what we have to do is we have to come up with 2x2 matrix. So identity, now we have to consider what y does. X went to x, y went to y, because identity does nothing. So now we can't break these things up. So we have to ask what 2x2 matrix takes the functions x and y and goes into itself. Well, that's the identity matrix. It's 1s across the diagonal. Now this is where the traces actually get interesting, right? We take the trace of this matrix and we get chi of identity equals 1 plus 1. The sum across the diagonals, the trace or the character, that's why it's called character tables, equals 2. That's why it's called character tables. So that gets us a 2 here, which we already knew from our other character table rule. The sum of the squares of the diagonals is equal to 16 that we did in the beginning. But now it's going to help us get the other characters here. So what 2 by 2 matrix takes x, y for C4 and goes to y and negative x? Well, that's going to be 0, 1 on the off diagonal, negative 1 and 0. And so we take the sum of this matrix and we get 0 plus 0, 0. So now we know our value up here, down here, I guess I should say, is 0. All right, the character under C4, 0. What about C2? Again, we're asking what happens to the x vector and the y vector. We have to do both kind of simultaneously here. And so, well, if we have a, let me just mark these properly here. If we have a x vector and we do a C2 180 degrees spinning along the z, that's going to spin x into the negative of itself, right? And same thing is going to happen for y, very similar thing here. We have a y vector, it's going to spin negative 180 degrees into the negative of itself. So we're going to have x going into negative x and y going into negative y. That 2 by 2 matrix is going to be negative 1s across the diagonal. That's the matrix that explains how x, y goes into negative x and negative y. You take the trace of that matrix and you get negative 1 plus negative 1, right? The sum across the main diagonals equals to negative 2. So our character of the trace of the matrix, character under C2 is negative 2. Okay, now we got to do the next one, which is C2 prime. C2 prime, remember we defined as going along our x-axis. So if we're going along the x-axis, and we're doing a 180-degree rotation, but we're along the x-axis, it's not going to do anything to x. X is going to go to x, but y is going to go to the negative of itself. It's going to spin it over there, right? Because we're flipping it 180 degrees this way. So we went from there to there, okay? And so that matrix is going to look like 1, 0, 0, negative 1, right? That takes x, y going to x and negative y. And so we take the trace of that matrix, and we're going to get that the chi, the character of C2 prime operation, is negative 1 plus 1, which is equal to 0. So we put 0 under there. C2 double prime. C2 double prime, a little harder to visualize. One of the C2 double primes, remember, is bisecting. So we're doing a flip that way, okay? It's a 180 degrees flip. And what that actually does, a little hard to visualize, but that's going to take x to y and y to x. We're doing a rotation off axis there. And so it's spinning them like this, right? So that's going to interconvert those two. So x goes to y and y goes to x. And that's going to mean we have zeros on the main diagonal, ones on the off diagonals. That's how the matrix multiplications works. If you don't know where this is coming from, check out my videos on how matrix multiplication works. But the character, therefore, of C2 double prime is 0 plus 0, which is equal to 0. And so we got a 0 under the double prime. Our next one is inversion. Inversion's always a nice one because it kind of tells us some things. By definition, x, y, z goes to any arbitrary point, x, y, z goes to negative x, negative y, negative z. So that means that, well, x then goes to negative x, y goes to negative y. And so our matrix for this transformation is just going to be negative ones on the diagonal. And so we're going to get an answer here. I'm not going to write the whole thing out, but we're going to get an answer here of negative 2, right? It's negative 1 plus negative 1. Negative 2. All right, next one, S4. S4 operation is equal to a C4 followed by a sigma H. Okay? So, well, a C4, what did a C4 do? It took X going to Y, and then we do a sigma H. Well, remember the sigma H, that mirror plane, is in the XY plane. So that sigma H doesn't do anything, because both the X and the Y vectors are just going to go to themselves. They're in the mirror plane. So this sigma H part doesn't do anything. So really it's just going to do the exact same thing as a C4. And for that reason, we can know that it's the same character as a C4. So S4 operation is going to take X to Y and Y to minus X. And that's going to be the same as the C4, and the character there was 0. That's what we calculated before. So put a 0 down there. Sigma H. Sigma H, we just went over and we said that X went to X, it didn't do anything, and Y went to Y for both of these. And so that's going to give us the identity matrix, right? Ones across the board. When we have the identity matrix, then the sum becomes 2. Right? We take the character, the trace of the matrix there, we're going to get 1 plus 1 is 2. All right, and then our last two are the mirror planes. We have the sigma v. The sigma v, let me erase some of this in here. But the sigma v, we have as being defined as the xz plane. That was what we talked about. And so the x vector is in that mirror plane, so it's not going to do anything. So x goes to x. But the y vector is to the right of that mirror plane, so it's seeing itself at the left of that mirror plane, so it's going to go to negative y. And so we're going to get 1, negative 1, 0, 0. That's the matrix that describes that transformation of x, y going to x and negative y. When we take the trace of that matrix, we get 1 plus negative 1, which is equal to 0. All right, and then we have the last one, which is sigma d. And the sigma d was bisecting, remember, sort of there. So look at this, they're both vectors are looking at each other in the mirror plane. They're both 45 degrees away from the mirror plane. So that means that for sigma d, x is going to go to y, and y is going to go to x. So we're going to have ones off the main diagonal. That's going to be our 2 by 2 matrix. That explains how xy goes to yx. And when we take the trace of that matrix, we get 0 plus 0, so we get 0. So there we now have finished deriving an irreducible representation, or a third irreducible representation. That one took a little bit more work because it was two-dimensional, so we had to consider both x and y, but we figured that out. And the other thing to check, it's good to make sure that you're doing these things right, is remember another character table rule is that all of these components have to be orthogonal to one another. So their dot products has to be equal to 0, one normalizing for the number of representations in each number of operations in each class. And so I'm not going to prove to you right now that these are all orthogonal to one another, but they are. Gamma 1 dotted with gamma 9 is orthogonal. Gamma 1 dotted with gamma 2 is orthogonal. And gamma 2 dotted with gamma 9 is orthogonal. The dot products equals 0 when adjusting for the number of symmetry operations in each class. But you could do that for yourself. And we're going to be using that principle at the end of this derivation to get some of these last remaining irreducible representations. So we'll get practice doing it as well together. But that is one way you can check to make sure you got the right answer. But we do have the right answers, but these first three irreducible representations. In the next video, we'll continue going on, and we'll work our way through some of these other irreducible representations.